Hello, and welcome to another session on data mining. We've been talking about two different linear discriminants, the SVM and the perceptron, that are able to achieve quite good results when the data is linearly separable. So they can give us a boundary, a linear discriminant boundary that separates the two classes. But we've identified the common limitation of both of them. That is, they don't work in when the data is not linearly separable, right? So we want to overcome that, and we've in our demonstrations in this module we've seen that if we fold the space in which these examples occur, we are essentially able to go from linear classifiers, linear separation, linear boundaries to non-linear boundaries in the classification space, right? So we've seen how we can fold the piece of paper and make a single straight cut so that we are able to solve problems that were originally linearly non-separable. So we've done some demos, and I welcome you to play with that approach a bit more. But the main theme is once we do that folding, that really helps, right? And we've also related that folding essentially means that we have changed the concept of distance between points. Now, one way of changing the concept of distance between points is, of course, to fold the piece of paper, right? But what does it mean mathematically? Now, in terms of mathematics, what we can change the definition of distance between 2 points in two ways. One of them we're going to talk about first is the concept of transformations. So that is, if we have examples lying in our feature space, like, sorry, in this space, we have got a set of examples, each one represented in 2D by two different features. So if we have example X over here, this one, then we can represent it in two features, and that is the feature space representation of this example. But what we can also do is we can transform this example, this particular example, using a transformation, whatever that transformation can be. We denote it right now in general by this letter phi, so that we map that point, that x vector that is representing this example, into another feature space. So we're changing the concept of feature spaces here. Let's say if we've got two features over here, we can use this transformation to map those two features for a given example onto a different feature space. So this point, let's say, gets mapped to this point over here. So what that achieves effectively is if we do this for all of the points, and if we have 2 points that are this distance apart in this feature space, they can be this much apart in the transformed space. So I typically call the space on the right hand side the transformed space, and this I'll be calling it raw features. So if you could give a set of examples in for raw features, we can use a transformation to map those examples into a transformed space, and then that achieves that changes the concept of distance. So the two points that are far apart in the original feature space can end up being close together in the transformed space. So that has the same effect as folding a piece of paper. So this is the first way of achieving transformations, achieving those folds, and that we've seen that that can help us solve a linearly non-separable problem with a single cut or a single linear discriminant in the transformed space. So what we do is, if we are given a problem that is not linearly separable, we can first transform it, and then that changes the concept of the distance between different points in the original space, and then we can make a single straight cut in the transformed space. So this is how we can achieve, uh, we can use a linear discriminant that we know how to make, and we can use that to generate nonlinear discriminant boundaries in the original feature space. So what we are going to do next is we're going to take an example of this, but I welcome you to pause the video here and think about this concept before we move on. Okay. So in the example that we are going to do, we'll take four examples, four points. So this is going to be the exclusive OR example. We have a point over here, we've got a point over here, and then we've got 2 points over here and here. Let's label these points. Let's call this point 1, this point 2. Let's call this point 3, and this one point 4. So we've got these 4 points, and for each of these 4 points, we know their feature representation. Let's say these two are zeros. This point is 0, 0. This is 1, 0. This is 0, 1, and then this one is 1, 1. And we also know the labels for these four examples. Let's say the label for this one is -1, that's a negatively labeled example. And the label for this one is also negative, whereas the labels for these two examples, 2 and 4, are positive. So this is the famous exclusive OR classification problem, and we know that this is not linearly separable, and we can prove that mathematically by writing the set of constraints that if we have a linear discriminant, let's say f of x is equal to w transpose x plus b, since there are only two features, so let's call them w1 x1 plus w2 x2. So there are going to be two weights, and these are going to be the two features of a given example, x1 and x2, and then we get b, and this is equal to 0. Now, what we want is if we are to use this particular form to classify these examples, then what we want is for point one, which is which has a training label of -1, we want that point to be below the line. So we want f of 0, 0 to be less than 0. And we know that f of 0, 0 is going to be 0 multiplied by w1 plus 0 multiplied by w2 plus b, and this is going to be less than 0. So what that implies then is b is essentially less than 0. Okay? And we can do this for the second point as well, which is f of 1, 0, but we want this point to be above the line because its corresponding label is positive. And if you do that, you can probably put in the value, and we want w1 plus 0 times w2 plus b, and we want this to be greater than 0. And what that means is this is w1 plus b is greater than 0. So each of these points is going to give us a set of constraints. We've done that in the past. And there are a few exercises that I would like you to work on uh, that were given earlier. And let's say if we got 0, 1, then we want this to be greater than 0 as well. Sorry, point 3 was actually 1, 1. So we are actually doing it for point 4 over here. So for that, we get W2 plus B greater than 0. And then for the point 3, we get f of 1, 1 is we want it to be less than 0 because it's negatively labeled. Therefore, we get W1 plus W2 plus B less than 0. And if you work on these four constraints, you will be able to see that it is impossible to find a value of W1, W2, and B that satisfy these constraints. However, if we do a trick, if we use a transformation, and I'm going to talk about that transformation, then we will be able to solve this linearly non-separable problem. And this is what we are going to do here. So we've got these 4 points. It's the same example, it's just a neater version of it. Okay, so we won't be doing solving it with hand, but let's say we've got these 4 points that you see on your screen. It's the same exclusive OR problem. And we have seen that we're not able to solve it using a linear discriminant in 2 dimensions. But if we use a transformation that takes in the features of a given example, x1 and x2. So each example is represented in 2D space and maps them to a three-dimensional feature space. So let's say we give a single example in 2D, and this transformation spits out a three-dimensional vector. So the first dimension is kept as such. The second dimension is also kept as such, but it adds a third dimension, which is essentially the product of the first and the second dimension multiplied by square root of 2, which is not important to, and you can probably get rid of this if you want it to be easier. So the transformation is what it does is it takes a single point in 2D and maps the same point into a three-dimensional space. So we've got this transformation, and if we apply this transformation on the points that we were given, so we'll be, if we take it on example number 1, which is 0, 0, so this point over here, if we apply this transformation on this point, then we get a feature, get an additional feature, which is square root of 2 multiplied by the first 0 multiplied by the second 0, so we get a 0 over here. The labels remain the same. The important thing to remember is in these transformations, they would always be based on features. No labels should ever be involved, okay? So we have the second transformation is 0, The second point will be transformed to 0, 1, and since the product of 0, 1 is again 0, so we'll end up with 0 over here. The third point, we'll add another dimension to this, so it's essentially we're adding another feature, okay? And we see that we have a 0 over here because the product of these two is 0. And for the fourth point, for this point over here, for 1, 1, we get an additional feature that is 1, 1 and square root of 2. So that means what this transformation does is it maps our problem, which is originally in a two-dimensional space, into a problem in three-dimensional space. And what that allows us to do is the following. Now if we try to work out a linear discriminant in this three-dimensional space, then that linear discriminant will have this function form, and we can write the set of constraints that we have that we started off with. We can have 0, 0, 0, the first point, and if we put those 0, 0, 0 in this linear discriminant, because this is a negatively labeled point, so we want this f of x value to be less than 0, and that gives us this constraint b less than 0. If we use the second point, then we get this constraint. The third one gives us this constraint, and the fourth one gives us this fourth constraint, right? And then what this allows us to do is that these values that you see on your screen are now able to, we're able to solve this problem, this classification problem in this space using using this linear discriminant in three-dimensional space. And you're welcome to pause the video and verify this solution on your own. And what this has done essentially is that it has enabled us to solve the exclusive OR problem by doing a transformation and then using a linear discriminant. So we have been able to solve this problem. But if you think about it, it's not the exact same problem. The original problem was in 2D space, but we converted it to a problem in three-dimensional feature space, right? Using the transformation that was given to us. And then we solved that. But the good thing is, for any test point that is given to us, we can apply the same transformation because the transformation is, remember, not based on the labels, it's just based on the features. So we should be able to transform any given test point into this new feature space, and then we should be able to use these discriminant weight values to determine whether it is above the line or below the line, essentially allowing us to label it. So that's really nice. So transformations can give us, just like paper folding, they can allow us to convert a linearly non-separable problem into a linearly separable problem. So we already know that I'm sorry, we already know that in 2D space, if we make a linear discriminant, that would be a line, right? But we can't draw a line for this one. So, but if we change it to 3D space, we now can separate these 2 points of the positive class from the 2 points of the negative class using a plane whose equation is going to be 2x1 plus 2x2 minus 3x3 minus 1 is equal to 0. So this is the decision boundary in the 3D space. But we also know that each point in the 2D space in this original space is mapped onto a corresponding point in the other space, right? In this feature space. And that means the boundary that we have in 3D that can also can be mapped back onto the as a boundary in 2D space, and we should be able to see the discrimination between the two classes. And if we do that, this is the hyperplane that we get for this particular problem. The green points of one class are above the line and the other ones are below the line. I've also given you some code that we are going to next play with that will help you understand this concept in a bit more detail. But the summary of what we have done is, if you're given a linearly non-separable problem, we don't need to be scared. We can do a transformation and map into a different feature space, and then we can try to solve it. And it conceptually or intuitively, it maps to doing all of this maps to folding the feature space and making a single straight cut. So I hope you have been able to gain a good understanding of this. Next, we are going to discuss the code. Thank you.